Romeo.
Okay, yes, thank you. I'm real excited to be here, and I was thinking that if there's a real burning question, feel free to interrupt, but otherwise, we could have questions at the end, and through the chat or also through the vocal. So I'll talk today about, give a kind of an overview about NuScale technology, including some fundamentals of nuclear engineering technology, and talk about kind of with a focus on commercialization, and some of the timing and the regulations and how nuclear and NuScale in particular stacks up against the other sources of energy. And then we'll talk a little bit about some other nuclear technologies, other companies, and kind of try and make some predictions, but predictions are particularly hard, especially about the future, as you guys are, I'm sure, aware. So I wanted to tell you a little bit how I got into nuclear. I think, like many of you, I'm sure I recognize that energy is fundamental and existential to our society. And there's a lot of ways we can harness the resources around us for energy, and we convert them in their raw forms into the forms we can use. And I kind of like to think about all of them derive, from the four laws of physics of gravity, electromagnetism, and then the two nuclear, the strong and the weak. So for me, in particular, deciding what form of energy to get into, I would say that, as you know, as engineers, there's only trade-offs, and for me, energy density really resonated, and so that's what I chose to go into. Kind of like as a heuristic, generally the less input is gonna, so the more dense something is, the less life cycle pollution. Now, not all forms of pollution are equally hazardous, so we have to keep that in mind as well. So, but like kind of the way I explain it to people, and I'm sure you guys know this very well, but so I'll do it quickly. But when people ask about how nuclear works or whatnot, I say take a tennis ball and drop it from an airplane, and you get about 3 food calories of energy. So we could think about hydroelectric being, a very dense source of mechanical energy. Whereas if we take a tennis ball and fill it with TNT and explode it, that would be like 300 food calories. Whereas nuclear energy, if you take that tennis ball and you fill it full of uranium fuel that we use in the reactor, it would make about almost 100 million food calories. So as this XKCD comic shows, the energy density is quite different, logarithmically different. And then I would kind of like to joke and say, but if you do know about a source of antimatter, please let me know, because that would be the ultimate form of energy. So get the E equals mc squared. That tennis ball would be very productive. So NuScale is a nuclear powered, so we use nuclear fission as an energy source. So a long time ago, stars far away exploded, and it took multi generations of stars to explode to transmutate what was originally hydrogen into heavy metals such as uranium. And then so we dig uranium in the ground and enrich it and put it in the reactor core. Now, if you look, this is the whole module, and the nuclear part, where the uranium is at the bottom, and it's about the size of the height of the guy there next to the module. The rest of the module, which is almost 80 feet tall, 15 feet wide, it's all about getting that energy when you fission the uranium into smaller pieces. That it heats up water, and then to take that water and convert it into electricity through a steam turbine, that requires this huge module. But the nuclear part, here we see with the reactor core, that's just a tiny amount. The rest of the module is all about exchanging that heat through steam generators. We use helical coil steam generators, and then containing the coolant system and the reactor coolant vessel. So it's called here the reactor pressure vessel. So we use natural circulation. So the uranium, the fissions heat up the water rises and then falls down and goes through the steam generators and then comes back up to make another lap.
What's your name, Greenies?
I'm sorry, what was that?
Everyone mute yourselves.
Sorry about that.
Okay. Oh, no problem. And then, so normally that's where everything is going on. And the steam generators are connected to turbines, which you can't see here, but you'll see on another slide. And then in case of some equipment failure, there's a containment which is used to contain steam and radiation that can happen and postulate accidents from equipment failures, and we can talk more about that. So our idea is we put 6 to 12 modules in a big building called the reactor building, and then every 2 years we got to refuel the reactor. And so on the left side of this building, there's an area where we'd move the module with this crane that's at the top of the building, and then we take it to the refueling zone, put fresh uranium in. We change about the third of the core each what we call operating cycle, and then we move it back and operate for another 2 years. And to put that in context, this reactor building is the site plan in the bottom here, and then that's just one building. The other buildings house the turbines, and then some of the operation centers and some of the heat removal locations. So it's a pretty small area for, so if you have a 12 module plant, it's about 900 megawatts electric. That powers the city. I think of like 50,000 people as a guess to give you a feel. And that, those buildings are quite small relatively. So because of the energy density, you could have a nuclear site, on less than an acre. So a lot of traditional sites are really big, hundreds of acres, and there's reasons, pros and cons for that, but it doesn't necessarily have to be a large site. Just to say that.
So what is the output from one of those modules, those 76-foot high modules? How many megawatts do you get from that?
So we're quoting 77 megawatts electric.
Okay.
So from 250 megawatts thermal. So if there was 12 of them, it would be, I think if my math is right, around 920 megawatt electric from the one building.
Okay.
And this is just another kind of shot, a zoom in of the reactor building. I talked through it. Those modules, is where all the nuclear stuff's going on, and then the rest of the building is just about getting them refueled every 2 years. So one module goes every 2 years, so you'd stagger. There would be a module being refueled every 2 months. So compared to a large conventional PWR, so there's about 400.
Excuse me, are you going to talk about what you do with the waste fuel?
I can, yeah. We'll do that.
That's what,
at the end of it.
whenever you mention nuclear, that's what people bring up.
Oh, I agree. Yeah, so I'll definitely touch on that. So this is a conventional plant. There's about 400 in the world. They're mostly, all what we call pressurized water reactors, which is the same core technology as what's in nuclear power submarines or aircraft carriers, but they're just made a lot bigger to make a lot more electricity. So this is kind of a comparison. The core sizes are about the same. They're basically twice as big, but the steam generators are quite a bit bigger. That's these tall blue things. And then the containment, instead of being a steel vessel, like in our design, it's this very large concrete, so it says here 200 feet tall, 120 feet in diameter, and that concrete is like 3 to 4 foot thick, just to give you an idea. So they have one reactor core and make about a gigawatt electric, and our plant, the design is if you have 12 of these modules, 12 cores, you'd make about a gigawatt electric. And we can talk more about some of the pros and cons of each. So just kind of taking a step back, I think what makes nuclear special compared to other sources of energy like we talked about is the energy density, because it's off the charts there, and the nuclear physics. And so that creates what I call the 4 grand challenges of nuclear engineering, which are criticality. So that's about how pure the materials are and the geometrical arrangement, how close the purity is. Scalability, so heat is generated in a volume, but it's transferred through a surface area. So, in some sense, the bulk of nuclear design is actually heat exchanger design. It's getting that tremendous heat through surface areas. Another thing that's unique is decay heat. So when you flip the off switch, a nuclear plant doesn't just go off. It goes to simmer. So if you're operating at 100% power, when you flip the off switch, it's still going to be at like about 6% power for a while. And then eventually, maybe a year later, it'll be at 3% power. And so that requires cooling of some sort. And we'll talk about the choice between active and passive cooling. The fourth thing is you are concentrating radiation. And so I like to call it alchemy in action. We are making gold along with not just the periodic table, but the whole table of isotopes. And so, obviously, some of those decay away and some of them don't. And that's a big part of the waste question, which we'll address a little in the presentation. So for reactor safety, the big thing is the decay heat. So I'll just say conventional plants, they've chosen to have active systems to remove the decay heat. So they have to have electricity or on-site power to pump water in and take that decay heat away. Now, so what the NuScale design is because it's smaller energy density with higher surface area, it's able to remove that heat passively. So if we look at this, all the modules sit in this pool of water, and as you know, water is a very good source of heat removal. And so the first 3 days when the decay heat's highest, basically we assume we boil off all that water. And then as the decay heat goes down, we can just have air cooling. So by 30 days, when the water is gone, the decay heat's low enough that all is needed is just the natural air cooling. So this is why we say you can cool it indefinitely without sources of power. So to contrast that, like with Fukushima, that plant, it's one core, like 1,000 megawatts, or 1,000 megawatts electric, or 3,000 megawatts thermal. It needed active cooling, and the tsunami, it was designed for a tsunami of, I think, 15 meters, and the tsunami was actually 30 meters. That's the rough estimate of my memory. And so that tsunami, and the way they put the on-site power, they buried it underground, and the tsunami, took that away. And so they didn't have cooling, and they could really only go 24 hours without cooling. And so once that cooling was lost, then the decay heat was melting the fuel basically, and then some of that radiation then escaped, and it's obviously still a big mess now that's being cleaned up.
Didn't they have to pump water to cool the reactor, and they lost the cooling pumps?
Yeah, that's what I'm trying to say. Yeah. So they had on-site generators, or on this slide says DC power. Well, first normally you could just pull power from the grid, but the grid was gone because of the tsunami. So then the backup plan was the DC power, the diesel generators, and those got flooded and weren't working. And that's okay for 24 hours, but they couldn't get power, for longer. I think it was 72 or more hours. And then, so finally they were able to get power restored and actively pump water in, but that it was a little too late in terms of the fuel already being compromised.
Is there any temperature limit that you can't operate in a heat dome? That for your long-term air cooling, if you don't have any cool air?
You just have to derate. You just have to derate the plant accordingly, depending on what your ultimate heat sink is. So, sometimes some nuclear plants reject their heat because, as we know, the law of entropy, or entropy, the second law of thermodynamics, when you convert energy from one form to another, some of it's lost. So for us, we're only 30% of the energy from the fissions actually goes into electricity. So that 70% has to get rejected to the environment. So some plants use lakes, and as the temperature rises, they have to decrease their operating accordingly. So instead of making 1,000 megawatts electric, maybe they only make 900 megawatts electric. And that's complicated by the choice of the ultimate heat sink, of course. So you can design very robust ones, but that probably will cost more money.
Well, but looks like you're going to have to design for 3 sigma or more events, because nobody predicted that we were going to have 115 degrees of days. Sure. So if you were just running the 10 or 20 degrees above average for your calculations.
Yeah, that's a great point. Absolutely, I agree. Another aspect of safety, or what we talk a lot about, is risk. So that's the likelihood of a failure times its consequence. So to compare conventional plants, now these are what we call internal events. So it's not from an external event like a Fukushima, or a tsunami, or a hurricane, or an asteroid, or anything else. It's those external events can cause damage to the reactor, and they need to be considered. And so, for example, with Fukushima, it's easy in hindsight to criticize putting the plant so close to the water when it's when the word tsunami is Japanese in nature, and they've had historical tsunamis much greater than where the plant was put at. But so you do have to very much consider those external assumptions. We also focus a lot on the internal assumptions. So how the pumps work, what size they are, where the valves are, how many they are. And so we assume that they're going to fail, and then we take the likelihood of their failures, and then we do these big fault trees and kind of trace the logic of what would happen if they fail. And so from that, we come up with what we call a core damage frequency from internal events. And to put in perspective, for like operating plants, they're at this 10 to the 4 frequency, whereas ours is 10 to the minus 10 is the estimate. And again, I just want to stress this is from internal events only. But as you can see, it's a much more robust and resilient design. And then another thing to kind of point out about, that was kind of touched on with some of the questions is, that comes, I think, about like positives of nuclear, is the robustness and resiliency of it. Some of the things we talk about are being able to.
You've got black container, and if you want to hear the nuke thing, you can. There's a lot of virgin grape up there. You know what that looks like.
Okay, if you don't mind muting, if you're not on mute, please. So here's some of the things we talk about with resiliency. Climate change was noted. Also, security threats such as aircraft impact, cybersecurity, electromagnetic pulse. So these are just some of the things to also think about besides just the Fukushima type of events, or the 3 Mile Island. The 3 Mile Island event was basically an internal event coupled with some confusing operator instructions and equipment, and operators made some mistakes. So I'll leave it at that for now. So okay, kind of transitioning to commercialization. So UAMS is our current customer, our first customer. They're a group of utilities in Utah, and the idea is we build the plant at the Department of Energy's Idaho National Lab site. And the timeline for that, so we've started characterizing the site, so doing like hydrology and meteorological measurements. In 2024 would be the starting mobilization for construction, and then 5 years later would be the first module installed, and then you could install more modules with time. So this timeline is a big part of it is based on the customer's preferences. So in principle, this could be sped up a little. I'm not sure how many, maybe a couple years, say. Probably not any more than that. But I just want to say that this isn't necessarily just our timeline. It's the customer's timeline as well, kind of the merger of the two. We have, so if someone came in, like I was saying, then potentially we could go faster than 2030. So these are some of the people and countries we've talked to. I would say, one of the questions that you guys were interested in is, can nuclear plants like NuScale have a meaningful impact on the Biden administration's decarbonizing goals? And from my understanding, that is a 50% reduction from the 2005 emissions by 2030. And so, probably the answer to that is no, unless a lot of customers were extremely motivated. But if you look at like the IPCC goal of basically net zero emissions globally by 2050, I think nuclear and NuScale could have a meaningful impact on that. Especially, I think people don't realize, or it's not obvious, because people mostly talk about net zero by 2050, and that makes sense. You first got to get to net zero, but the IPCC also says that we need to suck out like 100 to 1,000 gigatons of CO2, and not just in addition to being net zero, to keep below like the 1.5 C to 2 C. So I think, one of the things I thought was interesting is, well, how would you suck out carbon from the air or the sea? Because the oceans and the atmosphere are in equilibrium. So you remove carbon from one, you remove it from the other. And I think, nuclear has the potential to help with that. So I calculated it would take about 50 plants running for 100 years, 50 of our plants running for 100 years, based on the current estimate for how much energy it takes to remove CO2. To remove that 100 gigatons, and not even 1,000. So it's going to take a lot of energy, carbon-free energy, to not only get to net zero, but also remove the carbon we need to stay below that threshold. So that we're regulated, and I think that's great. I think any industry that has high consequences should be regulated. Now, not, as I'm sure everyone who deals with regulations, we could argue how efficient it is and how smart it is, and that there's room for improvement in nuclear, no doubt. So we've submitted our design to the NRC in 2016, and last year they approved it. There's kind of a process that it's not like federal law yet, but it's basically a formality. So we have generic approval to build a plant if someone wanted to build it, but there's a kind of basically like a permit needed for any one site. They just need to make sure that site meets is within the envelope of our generic design. So basically, we're not. In 2016, we were regulatory limited in terms of speed, and I would say now we're not. We're customer and manufacturing and construction limited. So that's exciting for us for sure. One thing I hadn't touched on, two questions that may be interested to you. What's the life expectancy of a NuScale plant? We're currently designing it for 60 years, but I wouldn't. 20-year life extensions are very common, and so I would see if a plant was operating economically and well, there's no reason I wouldn't think that it could go 100 years or potentially even longer. But that's a long ways in the future, so we'll just leave it at that for now. The other question is that's kind of relevant here is what magnitude earthquake are NuScale designs built to withstand? And that's a complicated question, but the short answer is roughly, say, 7 to 8 magnitude on the Richter scale. Part of the reason that's complicated is each component, our design basis is each component must be less than 0.5 G. Now, different design components have different design components have different resonance frequencies and whatnot, and different sites have different spectrums. So we chose a spectrum or a series of spectrums that kind of bounds 80 to 90% of the U.S. potential sites. So there would be some sites that, as of now, the design couldn't be built at, but there's kind of lots of ways that we could either customize the building or change the equipment out a little so that you'd still be under the 5G, or maybe we'd raise the 5G a bit for that plant with, different concrete and rebars and effectively. So yeah, that's the general answer is, 80 to 90% of U.S. sites, but any one site, it would be more expensive, but could be customized. Okay, one thing I want to talk about that's kind of unique to NuScale, we talked about the safety, both the passive cooling and the internal events from the simplicity, basically. But the other thing is modular, so it's a lot small. Each module is smaller, so in principle that would mean the capital costs for if you just wanted a couple modules would be a lot less than a conventional nuclear plant. Plus, you can have the economies of scale of manufacturing is the idea. So, as I'm sure you're aware of the general phenomena of the learning curve, every time you double, if it's a manufactured good, every time you double the number of total widgets you've made, the cost of each widget goes down 10 to 15%. And so we see that with solar panels, and that's why solar panels have gotten 10 times cheaper in the last decade, which is truly outstanding and also incredibly predictable if you're going to build that many solar panels. And we've also seen it with semiconductors and everything else that I'm aware of. So this kind of shows our schematic of how the plant or the modules get built and put in the plant. Step one is produce them in a factory. Step two would be, step three would be step one and two would make them in a factory. Three would to ship it to the site. Four would be, and five would be to put them in the plant and operate. And you could, one cool thing about it, I think, is you could build a building and start with one module and be making electricity and paying down some of the debt that you used to build the plant. And then you could add modules as you desired, and so that could potentially be a way to more cheaply finance, because the interest on billions of dollars will adds up in a hurry.
How about the operating costs? How would, if you scale this up to where it was, comparable in size to a legacy plant, how does the operating cost compare? I know it used to be, it was very, very high for the legacy plants, and unless they've changed from what we experienced at Trojan, but how does that look? Yeah,
I'll get to that in a couple slides, and if I don't, please remind me.
Great.
So one thing I do want to show here is, all the equipment needed to effectively get the heat onto the grid, or the energy onto the grid, and you can see, hundreds of thousands of cubic feet square feet of buildings, hundreds of thousands of cubic feet of concrete, millions of feet of wire and cable, a lot of instruments. You can see why the capital costs are high for nuclear. This is a lot of equipment. And I'll compare, this is NuScale's current estimate for costs. So first I'll talk about a NuScale plant. So that's here on the left. So if you have the first one, we're saying it's going to be $74 per megawatt hour. But by the time you got to the nth one, so maybe n is 10 or something, it would be 45. So if we say, okay, we'll give the benefit of the doubt and we'll say it's 45 for NuScale, how does that compare to solar and wind? We're saying solar is at currently 30 and wind would be 37. So you can see NuScale would be definitely more expensive than those. So I do kind of want to hold that a little bit thought as we talk about some other externalities and life cycle costs, but definitely there's kind of.
Let me go.
Kenny, you're muted.
Kenny, we can't hear you.
Hey, Kenny, it's apparently you're using a phone for audio, is that correct? And the noises that were coming in were clearly from phones, and I'm the one that stopped on the audio. So you need to unmute your phone again.
What would you suggest, Ed?
Anyway, Kenny seems to be doing the thing that worked at the beginning, so I think he'll be all right in a minute. I'm sorry about that, Kenny.
Hi, can you hear me now?
Yes.
You bet.
Okay, that's really frustrating. Sorry, I don't know what happened. Yeah, so I was talking about operating costs. Does that sound right?
Yeah.
Okay, so my rule of thumb is for a 60-year plant, about a third of the cost would be the initial capital costs and some of the debt financing associated with that. A third would be to the fuel. So we got to refuel these one module every 2 years. And then a third would be operations and maintenance, and including security. So there are a lot less parts compared to a conventional PWR, but it's still significant. You saw on the last slide all the different valves and wires and whatnot. And so I think, and then the security in principle would be the same. So I think that's one of the big things the nuclear industry has struggled with and will struggle with, and it'll be difficult to compete with solar and wind that have a lot less labor, maintenance associated with it. So I think it will be lower costs than a conventional plant in terms of operation and maintenance, but maybe not significantly, and it will depend a lot on how the utilities run in particular. One of the things in the beginning was talked about was how much, there was like thousands of people at the site at a time. That's typically, for a conventional plant, that occurs when they do an outage. So that's when they refuel every 2 years. And then they also that's a good opportunity to do a lot of maintenance. So with our plant, because there would be smaller outages happening every 2 months, potentially it could be a lot smaller, more efficient staff. If, you know, say 20 people all the time instead of 1,000 people for 3 months every 2 years.
Do your costs for battery storage and offshore wind allow for also getting cheaper as they get more into use, or because wind and solar used to be up there too, but now they're not.
Yeah, that's great. Yeah, I think the problem people do when they make predictions is they don't, for whatever reason, they extrapolate linearly, and then they don't take into account feedback effects. Like the learning curve is inherently a feedback effect. So yeah, I mean, solar has gotten 10 times cheaper in the last 10 years, and so can batteries do that too? And how will that affect things? That's a great question. And I don't have an answer to. But as an go ahead.
Kenny, when you compare the cost per megawatt hour, it really isn't fair to you, frankly, to nuclear to compare with wind or solar without backup. And so you really, to be comparable, comparing apples with apples, you need to compare with solar with storage. And that's where and a lot of people don't acknowledge that, you know, there's an additional cost, whether it be in gas-fired, you know, turbines or some other means, pump storage, and there's a big expense in making the intermittent power sources comparable to something like nuclear.
Yeah, no, that's why I was comparing it to battery and offshore wind. If you get in the right places, it's a lot more consistent than the onshore wind.
Yeah, it still requires a backup, though. You know, unfortunately, that's the Achilles heel in this.
Yeah, I'm kind of two minds on that, and I'll talk a little bit more on the next slide when we talk about externalities. You know, if we look at if nuclear plants has made about 20% of America's electricity for roughly 40 years, and the amount of high-level waste, the used fuel, would take an area about the size of a football field filled with this used fuel, like about 20 or 30 feet tall. So that's a lot of electricity in a really small volume. Right now, uranium is so cheap, it's economic to just dig more uranium in the ground and then stack used fuel ever higher. Now, the government took on the burden of getting rid of this used fuel. They charge utilities a fee for every unit of energy they made, and they said they're going to take the used fuel, and they'll handle it. Then they did, I think it was a big blunder. They passed legislation that forced the used fuel to go to Nevada, and Nevada, I think rightfully so, said no. And so now that's stopped. That was a dead end, and they're moving to a more consent-based approach. And what I think is that that used fuel still has a lot of energy in it, and you could definitely, when uranium got, say, 10 times more expensive, you could chop that fuel up and put it in what we call a different reactor design, kind of designed to do that recycling. And you could use that fuel, and instead of having radioactive waste that takes millions of years to decay, you can actually convert it into waste that only takes like 1,000 or so years to decay. And so I think that's a kind of a no-brainer solution, and it'd be economical if the whole nuclear fuel cycle is economical way to get rid of the waste. But we're not there yet, and that waste does exist. But my kind of message would be, it's really, really small amount of volume.
How about what about the source of nuclear fuel of uranium? Is how many years worth does the United States say have that's actually mineable and usable? If I guess that's a function of how much generation you have, but.
Yeah, we could say roughly at current prices, say 50 years, but some of the best mines are just across the border in Canada, and they have lots there. And so, assuming we're in good terms with them, Australia has a lot of capacity, and then uranium doesn't actually have to get that much more expensive for it to be economical to mine it from seawater. And seawater is always getting more uranium from erosion. So yeah, so in that sense, it would be, I mean, really, it's an infinite supply if you're getting it from from seawater, and then you're recycling the fuel over and over again to get all that energy out that was put in there by the sun or the stars originally. So I'll kind of talk quickly about, there's a lot of other people doing nuclear in various ways. This is just some of the brands, and most of these are new, like us, but not all of them. GE and Westinghouse have been around for a long time. The thirdway.org says there's about 70 plus different designs and companies making designs, and they all have different shapes, sizes, and materials. So, anywhere from 1 to 300 megawatts electric, uranium enrichments of 0, or not quite 0, but I guess, 0, because you can use used fuel in some of these designs, to 20%. They're looking at uranium, thorium, used fuel, different materials to hold the fuel, different coolants. We use liquid water, but there's also liquid metal, molten salts, organic liquids, gas, and then different ways to moderate the neutrons, which is part of the nuclear physics. So they're all trying to solve called the 4 grand challenges of nuclear engineering, and there's a lot of trade-offs, and so far no one obvious winner. To kind of give some context, I could call the 40s through the 60s the age of nuclear exploration, and I think a great quote from one of the Atomic Energy Commissioners, which is basically our DOE now. He said, we seem to be designing almost everything except beer-cooled sawdust moderated reactors. And as you saw from that list, we're still doing that in various forms. At Idaho National Lab alone, there was 52 test reactors, and then there was a bunch of private test reactors as well. So Fermi 1 was a privately funded sodium-cooled fast reactor. Fort St. Vrain was a gas-cooled reactor. I think the CV, I think it stands for Carolina, Virginia tube reactor. It uses organic liquid, so like a non-flammable, fluid, organic fluid. So that was all just the United States, which was the leader, but there's been a lot of experimentation in other countries as well. Then, like I was saying, basically all the 400 reactors operating commercially in the U.S. are basically the same technology as the nuclear navy. I think there was lots of factors for that, not just one. It wasn't just the technology. So I can't really say what I think will happen in the future in terms for these SMRs, but it's not like these other designs haven't been explored a lot. So I kind of wrap up by saying what makes NuScale special and some of the trade-offs and the pros and cons is it's the very high surface area relative to the power density. So that way we don't need power to cool the reactor. So that makes it resilient to things like Fukushima type events. It also uses a lot of digital instrumentation control, which makes it easier to operate and cheaper and safer. And then the design has been, risk informed. So we have a lot less parts, and we put the parts using the best insights of the probabilistic risk assessment. So that internal damage number I was talking about, that a big part of the reason that's so low is because we took that into account while we were designing the plant. For economics, the learning curve, if unlike nuclear, our conventional nuclear that was all custom built on the site, we want to make as much as we can in the factory. We're going to still be pouring concrete at a site, and that's caused a lot of problems with conventional nuclear, and so that would apply to us too. The biggest reason, like that Ocolido plant in France, or it's a French design in Finland, it was like 10 or 20 years over schedule. They poured the concrete wrong, and then there was legal battles, and it's a mess. So we've got to, for our plants, we've got to pour the concrete right, and there can't really be any mistakes there for us to be, for our reputation and for to be economically competitive. So that's just something we need to know and do right. We are the only current SMR with US NRC approval, so we're no longer regulatory. Time scale isn't the problem. It's limiting. It's our manufacturing and customers paying for the manufacturing. And then for NuScale, for nuclear generally, I kind of think it could go two ways. NuScale is an incremental improvement. It's not an evolutionary leap. So will nuclear, if nuclear keeps going, will it be incremental or will it be a quantum leap? And it's hard to say, and I don't know. But I'm obviously in the incremental camp, I guess you can tell, because I've been in NuScale for 9 years. So that we got some chat questions. If that would like me to answer those or talk about those.
Kenny?
Yeah.
Before you go through the chat questions, I'd just like to say that on August 26th, we're going to have another meeting at noon, and Jack Kerfoot will be discussing concerns that we have about the Zenith oil terminal. And so you might all want to reserve some time for that. And if anyone wants an hour's credit from their engineer's license, please email Mike Unger at Comcast.net. And Kenny, I think it's okay if we hand out your PowerPoint. Is that correct?
Yeah.
Okay. All right. Yeah. So excuse me. Go ahead now with the chat questions.
Okay. So the effective capacity of the plant, so typically nuclear plants are baseload, and so a common industry is about 90+% capacity factor. So that means it's operating full capacity 90% of the time. You could, if the economics made sense, you could load follow, is what we call it. So you could reduce capacity for solar and wind, and we're doing studies on that to show and demonstrate how it would be and frankly see the trade-offs, like how much does it cost, and is there a way you can use the uranium and not waste it? And there are ways. So, but if the labor, if you're going to have the operators on site and the security force on site full time, even if the plant's not running or it's running only partly, it would kind of make sense that you'd always want nuclear to be baseload. But if the price of being on standby was high enough, then maybe it would work. So I would say the answer to this question is it's as whatever the customer would want it to be, which could include, you know, effectively 100%.
Can you modulate the output from these units to complement the intermittent sources?
Yeah, there's several ways that could be done. We could reduce the core power for a while. We could send some of the steam to the condenser, and so that would be less to the turbine. You could also take a module offline. Would be another option.
Okay.
Another question is, assuming the licensing of the plants goes well, what's the approximate megawatt hours compared to a new fossil fuel plant? And so I'd go back to that slide. We say conventional fossil, which I would say that, you know, these natural gas plants, you know, it's hard to say with the fuel, that is volatile. Well, it doesn't really say, this doesn't have a good saying. It's kind of more advanced fossil fuels, not like a conventional coal or even a conventional natural gas. So I'm not sure what those numbers are, but we're saying 74 for the first one, and then the nth of a kind would be 45 is the estimate. And then next question is, the initial fueling of the module done on site? The answer is yes, all the fueling would be done on site. What we do is we build the building, put the module in, and then basically do 3 to 6 months of all sorts of different testing, pressure, temperature testing, and then we put some fuel in and do a little bit of increase the power a little, and then do some more testing and make sure that the fuel and all the measurement devices are working appropriately. And that would take a common amount, especially for the first plant, could easily be 3 to 6 months. And then a question is about climate change. I would say, yeah, most from what I read, including, you know, I think the IPCC is a good reference, that people say that we need all of the above to get to net zero by 2050 and burn and suck carbon out of the air as well. We'll need energy to do that. So yeah, so I'm for all of the above for sure, and I'm a huge fan of solar and wind as part of that, and I obviously think nuclear can play a role too. The next question is, what can I say about the design safety questions left unresolved in last summer's safety certification process in regards to emergency shutdown? I think that's in regards to what I would call a postulated event with basically could there be boron diluting in the reactor coolant system under a certain set of circumstances? It basically be kind of like the way the natural circulation and the valves and everything works. You could postulate that you could kind of distill out the boron, and we use the boron because it captures neutrons, and so it keeps the reactor shut down. So it helps us keep the off switch off. And so the ACRS is they're the oversight committee that oversee the NRC's review. So the regulators are the NRC, and then the ACRS, they do a lot of meetings and reviews of the NRC's work as another level of the regulatory process. And they had some questions, and they were good questions, and as a result, we discovered that one of our assumptions was bad, and so we didn't predict this event trajectory. We didn't predict that this boron could potentially be distilled. So what we did was we changed the design slightly to make sure the boron will mix. And so I would say that it's completely resolved. The NRC is happy with that. The ACRS is happy with that. And so I would say that that's completely resolved. The next question is, does NuScale have a pilot plan? Does operational approve its operation? No, we don't. That would, the capital costs we're quoting, are like, depending on, we're saying for the heat removal capability that UAMS wants at the INL site, we're saying that plant would cost like $6 billion. There's variations of that might be like $4 billion. And so that's just a lot. It's a big test. And we have a thermal hydraulic test at OSU, the Oregon State University, that we do testing on for specific thermal hydraulics, and we use that to make sure that all of our analysis or those types of analysis codes are correct. But it wouldn't be like a pilot plant at all. So we don't have any plans for a pilot plant. We wish we could in a sense, but it's just kind of the nature of nuclear, where your first plant is your pilot plant. The last question here is about, so far as brittle metal causing problems with nuclear. Is that true, and what's better about NuScale? Well, I would say, like, the nuclear engineers are always a slave to what chemical and material engineers and material scientists can give them to work with. The 4 grand challenges of nuclear engineering, as I call them, they're all about materials. And if we had unobtainium, we could make the most scalable, perfect nuclear design. But we don't have that. What NuScale does have is we are an incremental step of traditional PWRs, which have a lot of operating experience. So traditional PWRs have had embrittlement, and they've taken those lessons learned to improve that in their plants. Sometimes it means changing the chemistry. So they'll add lithium and some other elements into the reactor coolant system. They also spend a lot of time keeping the reactor coolant system really clean, so that you don't get the right amount of cations and anions, and if those are the right terms. I'm speaking a little bit out of my area, but they keep it clean so that's not a possibility. So I would say brittle metal is always going to be an issue, especially with radiation damage. But NuScale has the advantage of learning from all that experience, and it's not an extrapolation as much as an interpolation. And so we've learned from that, and that's the best way I could answer that question.
Well, thank you, Kenny. Greatly appreciate your time and preparation. It's very informative.
Yeah, we wish you the very best of luck with your plant there and your ability to commercialize that technology. And we're looking forward to hearing about it as we go forward. Maybe we'll have you back here and at some point in the future, and you can update us.
Yeah, it sounds great. I really appreciate everybody's attention and good questions, and I would love to.
Okay, so our next presentation will be August 26th on the Zenith Oil Terminal. And then, Bob, we have one the second Tuesday of September, right?
That's correct. Yeah, we're going to have a presentation from the Northwest Power and Conservation Council. and they're going to be, can you hear me?
We can.
And they're going to be talking about their organization and how they see the Pacific Northwest responding to the Biden goals. And it should be a very interesting talk. They're kind of a coordinating body between a lot of the utilities in the Northwest. Well, that concludes it for today.
Thank you.
Thank you.
Thanks for putting it together.
Now, thanks again, Kenny.
Yeah, thank you.
Appreciate it.